Hello, and welcome to CS492G, Foundation and Future of Virtual Reality, Artificial Intelligence, and Massively Multi-User Online Role-Playing Games. The semester is approaching its final weeks, and also this course is about to come to an end. We're in this week listening to the final two talks of the third and last part about MMORPGs, namely about the foundations of distributed memory and distributed computer systems. So this is every part, each of the three parts had some philosophical aspects, some social aspects, and some technical and some theoretical aspects. And this is what we're going to hear about today and on Thursday. And this talk will be given by Go In-hui. So let me remove my spotlight and give the spotlight, the attention, and the microphone and the screen sharing to Go In-hui. Here you go.
Okay, good afternoon. Could you guys hear my voice? Yeah, well, I think that you can hear my voice. So yes, okay, great. So good afternoon, everyone. And can you guys see my screen too? Yes, okay, great. So I'm going to start now then. Good afternoon, everyone. My name is In-hoi Koo, and I'll give a presentation on distributed computer systems. So this is an index of today's presentation. I'll cover until the third part, PRAM problems until today, and go through the other part on Thursday. I'll start with the introduction first. Scalability is the key of MMORPG. With better hardware performance, a faster network, and the evolve of the metaverse, MMORPG relies more and more on the efficiency of computing. As user computers exist independently, MMORPG could scale using each computer as a computing node and creating a parallelly executed environment. On using a parallel algorithm, there are two design questions that has to be considered first. The first question is, does problem has enough parallelism? This question has nothing to do with the parallel model we choose, but the parallel problem we want to solve itself matters. On MMORPG, as each computing node is independent, we can say that the problem itself could provide enough parallelism to be solved with a parallel algorithm. The second question is whether data sharing is fast enough. This is closely related to the parallel model we choose. As data sharing consists of accessing the shared memory and getting the data via network, we have to consider how to share data with high efficiency on the memory and on the network. This problem will be handled on this presentation later on. Before we move on to the details, I would like to review the concept of asymptotic notation. As you would have all learned on the algorithm class, there are some basic terms that you should know and will mainly be used on this presentation. The first and the most widely used notation is the big O notation. It is used like the expression above, and it means if certain function f is big O of a function g, it means that f grows asymptotically no faster than g. The first figure on the bottom explains this situation. You can see that a function f of n grows no faster than a function g of n after some point. The second is the big omega notation. If certain function f is a big omega of g, it means that f grows asymptotically no slower than g. The second figure illustrates this situation. A function f of n grows no slower than a function g of n after some point. The third is the big zeta notation. If certain function f is big zeta of g, it means that f grows asymptotically as fast as g. The third figure illustrates this situation. A function f of n grows as fast as function g of n after some point. Also, Amdahl's law is one important law that you should know in order to understand parallelism. Amdahl's law could be used to explain various cases, but here I will mainly focus on the parallel environment. On a parallel environment, there are some parts that could be parallelly executed and some parts that should be sequentially executed. On Amdahl's law, no matter how much you can speed up the parallelly executed part, the overall speed up is mainly defined by how small is the portion of sequentially executed part. This could be explained using a simple example with the figure below. Let's say that the orange part is sequentially executed part and the blue part is parallelly executed part. So on the first case, the sequentially executed part is 10% and the parallelly executed part is 90%. And on the second case, the sequentially executed part is 50% and the parallelly executed part is 50%. So here, I'll give you a simple quiz. If the speed up on the parallelly executed part is 3 times and 10 times each on a first case and a second case, which case do you think will have a bigger overall speed up? So yeah, this is a quiz, and if you could type the answer, could you please type the answer on the chat, please? So to elaborate my this quiz again, so the left part has 90% of parallelly executed part, and the right case has 50% of parallelly executed part, and the speed up on each parallelly executed part is 3 times on the first case and the 10 times on the second case. So which one of these two will have an overall better speed up? Yes, okay, so you guys are all right. So the answer is the first case. On the first case, if the speed up using parallel algorithm is 3 times, the overall speed up is 2.5 times. However, on the second case, if the speed up using parallel algorithm is 10 times, the overall speed up is only about 1.8 times. As you can see from the figure, no matter how much you can speed up on the parallelly executed part, because sequentially executed part cannot speed up at all, the overall speed up is decided by the portion of the sequentially executed part mainly. Next, we'll cover the concept of parallel random access machine. Parallel random access machine, or PRAM in short, is an example of parallel computation model. The figure below explains the concept of n, m PRAM. This means that this PRAM consists of n processors and m memory locations. The memory is shared by all processors, and on a single cycle, processors could either read or write using a shared memory and a local memory, or compute a data on a local memory. There are three kinds of PRAM depending on the memory access pattern. These three PRAMs vary on if various processors could access the same memory location on a single cycle or not. The first PRAM, EREW PRAM, or exclusive read, exclusive write PRAM, can only have one processor that could read or write to a single memory location at a cycle. The second PRAM, CREW PRAM, or concurrent read, exclusive write PRAM, can have many processors that could read to a single memory location, but only one processor could write to a single memory location at a cycle. And the final PRAM, CRCW PRAM, or concurrent read, concurrent write PRAM, can have many processors that could read or write to a single memory location at a cycle. EREW PRAM has the smallest complexity, but it has the smallest computing power, which means that some algorithm would take more time to run on a EREW PRAM. Likewise, CRCW PRAM will have the largest complexity, but will have the largest computing power among all. Comparison of these two PRAM with example will be handled later on. On a CRCW PRAM, there are four conflict resolution strategies. The first strategy is common CRCW PRAM. In this case, all conflicting written values should be identical, or else there will be an error. The second strategy is arbitrary CRCW PRAM. As the term arbitrary tells, the value chosen is random from conflicting write values. The third strategy is priority CRCW PRAM. Here, the value chosen on a conflict is the value whose processor has the highest priority among all conflicting processors. The final strategy is combining CRCW PRAM. The value chosen here is the linear combination of all values that are written. So the linear combination here means that the values could be added or subtracted, or else another linear combination examples. Although this strategy is the most ideal strategy compared to other strategies, it is hard to implement in reality. Here, I will show you how powerful, in other words, how fast parallel algorithm using PRAM could be. The time complexity of PRAM algorithm matters on what kind of PRAM you use. First, I'll show you how sorting algorithm could be solved on a EREW PRAM and CRCW PRAM using closed parallel merge sort. On EREW PRAM, sorting could be done in a big O of log n time using merge sort, which is much shorter compared to common merge sorts, which takes big O of n times log n time. This parallelism comes from the binary tree-like approach. Since the proof of this is pretty difficult, I'll just roughly go through this. On a normal merge sort, values had to be compared one by one while merging. On a binary tree-like approach of merge sort, comparing every twice integer, so the ith one and ith plus one on each processor could compare several values at once. Therefore, on a total merge sort, you can do this each step in a big O of 1 time instead of big O of n time like normal merge sort. Also, then we can compare every fourth integer, ith one and the ith plus 2 one on each processor to sort the next value. So in total, this iteration will need a total depth of big O of log n. In summary, since every level of merging could be done in a big O of 1 time using binary tree-like approach, And since the depth of merging is big O of log n time, the total sorting will take take big O of log n time. On a CRC-W PRAM, sorting could be done in a big O of log n divided by log time log 2p divided by n time, where p is the number of processors that is in between 2n and n squared. This is smaller than big O of log n time, which is achieved by the EREW PRAM. Since the proof of this is complex and difficult, I won't discuss this in class, but you can see that the time complexity of PRAM algorithm is efficient compared to non-parallel algorithm, and that the time complexity vary by the type of the PRAM we choose. Also, on a CRC-W PRAM, depending on what conflict resolution strategy we use, there could be some algorithm that could work and that could not work. One example problem is finding the maximum value. An algorithm that could solve this problem in big O of 1 time is as follows. By using n-square processors, we can compare every subset of 2 elements and write 1 on the one with the smaller value. So for example, if the two values are 3 and 4, we are going to write 1 on the 3. Then, if we use n processors to check the element with value 0, then that is the maximum value since it has never been smaller than any other value. This algorithm could be solved using combining CRC-W PRAM. We can simply add all the values that are concurrently written. However, all the other conflict resolution strategy will have a problem using this algorithm. For example, common CRC-W PRAM needs a guarantee that all the values are identical, which could not be true here. Arbitrary CRC-W PRAM chooses an arbitrary value, so we won't find out what has every value of 0, since in some cases where 1 and 0 are mixed, it could be seen as a 0 after all. Like this, the conflict resolution strategy affects what problems could be solved or not using a specific PRAM algorithm. Then, we will look into the problems we have to solve on PRAM in order to apply PRAM to realistic machine. As we've seen on the previous slide, PRAM is powerful and general, but also simple. However, there is a problem that should be solved in order to apply PRAM into realistic machine. Since current machine does not have a shared memory that is shared by numerous processors, more realistic parallel model uses set of processor and memory module pairs that are connected with sparse network of links. Here, we will define PRAM simulation problem as how much slowdown occurs on a simulation of a CRC-W PRAM into a realistic parallel machine that I mentioned before. PRAM simulation problem could be divided into 3 subproblems. Before explaining about these 3 subproblems, I will explain about 4 parallel models from the most ideal one to the most realistic one. The most ideal model is CRC-W PRAM. The next ideal model is EREW PRAM. And there is the model parallel computer, or MPC in short. Model parallel computer uses set of processor and memory module pairs, but they are connected with fully connected network, which is infeasible. Finally, the most realistic one that could actually be constructed is the bounded degree network, or BDN in short. This model uses bounded degree network instead of a fully connected network compared to the model parallel computer. Then, we can talk about the three sub-problems. The first problem is the concurrent access problem. It could be seen as decomposing CRC-W PRAM into an ERE-W PRAM. So, this problem will focus on the slowdown that will happen from running a machine that could concurrently access memory to that could not concurrently access memory. The second problem is the memory management problem. It could be seen as decomposing ERE-W PRAM into a model parallel computer. This problem will focus on how to lay out memory so that the amount of module contention will be minimized. And the final problem is the routing and the interconnection problem. It could be seen as decomposing module parallel computer into bounded degree network. So this problem will focus on the algorithm that will minimize the slowdown while servicing on a fixed degree network. These three problems in total will create a model that could estimate the slowdown from CRC-W PRAM into a bounded degree network, which we call PRAM simulation problem in total. The quality of PRAM simulation is mainly assessed by the slowdown. Slowdown here means that how much more steps are needed when simulating a single model onto a different model that is more realistic. So, the slowdown of total PRAM simulation problem would be additional steps needed from executing a program on a CRC-W PRAM into executing a program on a realistic parallel machine. On a mathematical expression, if the steps needed for a CRC-W PRAM is t, and the steps needed for a realistic parallel machine is fn times t, f of n times t, then the slowdown will be f of n. There is also a metric called efficiency. Efficiency means the ratio of time needed regarding the number of processors. If the time needed is independent from the number of processors, then it is called as optimally efficient simulation. This case will be the most desirable case because no matter how many processors exist, this won't need any additional time, and therefore we can call this case scalable. Efficiency on a PRAM simulation will be discussed next class. Concurrent access problem is to see how much slowdown happens when several processors can concurrently access single memory. In other words, it could be seen as simulating CRC-W PRAM into an ERE-W PRAM. The optimal slowdown of concurrent access problem is as follows. There are three steps in total. The first step is to sort the memory request by its requested memory location and the requesting processor. As we discussed before, this could be done in a ERE-W PRAM with the time complexity of big omega of log n time. Then, processors should choose how to handle concurrent access on the same memory location. In this case, any conflict resolution strategy discussed before could be used, but using combining CRC-W PRAM, which uses a linear combination of all values that are written, would be harder to implement. Using other conflict resolution strategy would be much easier to implement. Handling concurrent access on the same memory location could be done efficiently using the binary tree approach with which we used to implement merge sort. So with binary tree approach, it will take big O of log n time to check all the concurrent access on the same memory location. Finally, on a read, if there are several processors accessing the same memory location, multi-broadcast will be needed. And this could be done in a big O of log n time on a parallel computer. Overall, as every step combined requires at least and at most log n time, simulating a CRCW PRAM on an EREW PRAM will need a slowdown of big zeta of log n, which is the optimal slowdown on a concurrent access problem. So this is the end of part 1 and end of today's presentation. Thank you.
Thank you very much for this presentation. And before we proceed to the discussion, maybe you want to briefly recall 3 to 5 key take-home messages from today's talk, and also give a perspective of what to expect next time.
Okay, so on today's class, we had some introduction slides about parallel computing. So we learned about, we learned about Amdahl's law. And another important point today is parallel random access machine. So this is, although very theoretical, but it can be used to implement algorithm that works really fast, but has little complexity. And also we learned several kinds of PRAM depending on the memory access pattern and on the conflict resolution strategy. And yeah, I went through some PRAM algorithms and showed that PRAM algorithms could be done very efficiently. And then I discussed how to simulate PRAM into a realistic machine, and show that simulating PRAM into a realistic machine involves 3 problems. And I gone through the first problem among these 3, so the concurrent access problem. And next time, we'll go through the simulation of other 2 subproblems. So the memory management and the routing and interconnection problem. And each subproblems will be solved using deterministic and random algorithm. And I'll go through both cases with simple proof, or if the proof is so complex, then I'll just introduce you the theorems. So yeah, this is what I presented today and what I'm going to present next class.
Thank you really. So now we're going to take a short break, maybe like 5 minutes, to allow you to digest today's presentation and to come up with questions and comments regarding the content, not regarding the style or quality. That's we'll discuss separately. So please take this break to come up with questions and comments about the content. And here we are back online to start the discussion and to answer questions about the content of this talk. And just to give you a perspective, for those of you who have attended CS300 Introduction to Algorithms, where I keep emphasizing the importance of abstraction, right? So computers are based on transistors, and transistors you heavily use quantum mechanics. But as programmers, we don't need to care about quantum mechanics because there are so many layers of abstraction on top of that. The bits as abstraction of quantum mechanical currents, then there's bytes, then there's operating system, and on top of all that, there's high-level programming languages. And what InhuiGo presented today is an extension of that. And in CS300, they learned that sorting requires n log n time, but that's of course sequential time. And the PRAM extends all these considerations from introduction to algorithms to parallel computation with these very nice and very structured models of computation and the problems of simulating one on top of each other, so that in the end one can resort to simply devising algorithms for the most convenient model. And their most convenient model is the concurrent read, concurrent write PRAM, where one can, for example, calculate the maximum in constant time. And I bet you wouldn't have been able to come up with a constant time algorithm for computing the maximum without all this abstraction. If you were just asked to compute the maximum in parallel time, I'm sure you wouldn't have come up with constant time algorithm only using this abstraction and the layers of simulations. That's the power of abstraction that enables creative design of algorithm. So long story short, now is your time, your chance to ask questions and to give comments about the content of the talk. Here you go.
Okay, so I shared the slides again. So yeah, if you have any questions, yeah, I'll be welcome to get those questions. Yeah.
Yes.
Okay, so there is a question on the chat. So can we think combinational logic as one of example of PRAM? The electric writes are basically concurrent. So combinational logic. Combinational logic. Wait, I'm a little bit confused about the term combinational logic. Wait. Could you please elaborate on the definition of combinational logic, please?
So
Yeah, I get it. Okay. So, wow, this is a pretty nice question. But I don't really think combinational logic could be seen as an example of PRAM, because in order to be a PRAM, there should be several processors. So processors could do any general things, but actually the electrical wires are hardwired, so they could do like some things that are supposed to do. And I think that is the difference. And so this is the biggest difference, because on a PRAM, there should be a shared memory that can be accessed by each processor. But on a combinational logic, some kind of wire is just connected to a different, yeah, so a single wire is just connected to a single memory space or a register. And so, yeah, I think because of these differences, I think it will be really hard to see a PRAM as combinational logic as a PRAM.
Right. So for those of you who attend or have attended my course CS300, there we did talk about sorting in parallel, right? And we use these sorting networks. And you can imagine every single sorting node to be one very stupid processor. So the PRAM is kind of a generalization of that, where each node is much more intelligent than just comparing and swapping as in sorting networks. More question? Remarks?
I have a question.
Oh, yeah.
So, do you know any historical backgrounds of these developments of such an algorithms? Why these problems emerged and what were the prototype solutions for those problems, etc.?
Okay, so this kind of parallel random machine is some kind of a thing that many researchers on these theoretical backgrounds on parallel computing want to try. So these algorithms, any PRAM algorithms could be changed into a, so, okay, so yeah, I'll start again. So since parallel computing became able from like multiprocessors and other ways, researchers started to think about how to use these parallel computers and have a speed up as much as they could. So as you see in the MDES law, if there are many sequentially executed parts, then that would be bad to the overall performance. So people thought, how can they parallelly execute everything as much as they could? So that is the approach why researchers thought about parallel random access machine. So this is a simple model, but also a very powerful model. And the only problem on this PRAM is that it couldn't be built in reality because of the shared memory problems. So if you devise an algorithm that could run on a PRAM, then it is known that these algorithms could run on a realistic parallel machine at a log n, big O of log n big O of log big O of log n cost that we will discuss later on. So with this, if you could devise a new algorithm that you want to work parallelly and get some better performance, you can use that to make an algorithm on PRAM, which is much simpler than just devising an algorithm on a realistic machine. So yeah, I think this is the theoretical background of PRAM. So yeah, on timing, on years, this PRAM was developed around about late 1980s, and as I know of, it is getting research until now maybe, but yeah, I'm not really sure about that. But these kind of parallel model and parallel machine was mostly well organized on the late 1980s. Yeah, you're welcome.
More questions? comment? Yes, you will still have time to ask questions and to give comment on the content after the second part on Thursday, right? So on Thursday, we're going to have the last part of this presentation in spite of the undergraduate admission interviews. So please, everybody, join on Thursday. And so that being said, let's now proceed to give feedback on the style and quality of the presentation. And as usual, this is going to be off the record, so I will turn off recording now. So thank you very much. And to wrap things up, that's all for today with the first part of the presentation, and we will resume and continue on Thursday. So class is over for now, and yeah, everybody feel free to log out, except for those who want to talk with me individually. Please feel free to stay online for some additional chat. Okay.
Thank you.